Hello, welcome to the video demonstration of my EE373 final project, omnidirectional control of a two-wheeled balancing robot. My name is Tianhao Zhang, and a detailed description of this project is contained in the PDF project report. The core challenge we address is twofold: non-holonomic constraints and the nonlinear coupling of physical variables, which makes stable omnidirectional movement a significant control problem. This is the successful navigation of our final DRL agent, demonstrating PBO's proficiency. Okay, before diving into deep reinforcement learning, I established a baseline using a classical control approach, a cascaded PID controller. I designed an uncoupled architecture with an outer velocity loop to compute a target pitch, which guides an inner pitch loop for base torque balancing. A separate yaw loop computes steering torque for heading control. The pros are evident. It is efficient in linear regimes and longitudinal stability, as seen here in Demo 2.1, tracing a straight line. However, the cons are significant. There is a catastrophic failure during aggressive yaw maneuvers. Because the controller is blind to 3D physical cross-coupling, turning past certain angles leads to an immediate loss of balance and spin out, as demonstrated in Demo 2.2. Transitioning to deep reinforcement learning was a journey of trial and error. I encountered interesting pitfalls along the way before arriving at the final solution. Well, you can find the solution in my PDF report. For instance, the version 7 model fell into the endless gyro loophole. This is a classic case of reward hacking where the agent exploited the gyroscopic stability reward, spinning endlessly in place while completely ignoring the velocity target. Then came the version 10 suicidal paradox. The penalties for instability were so high that the agent found falling over immediately, the death preference, was the most efficient way to minimize long-term penalty. Even the version 36 model, as progress was made, suffered from unhandled cross-coupling during turns, leading to uncontrollable oscillation and an inevitable crash. The ultimate dynamic resilience was evaluated in these final disturbance tests. We applied a front push at time step 400 and a much more dangerous unmodeled lateral push at time step 800. Notice the baseline cascaded PID controller on the top. While it is strong in the longitudinal direction, it is completely blind to 3D physical coupling. The lateral push immediately defeats it. Now compare that to our final DRL agent on the bottom. It demonstrates excellent dynamic resilience. When hit by the lateral push, it starts violently bouncing, but it successfully recovers its center of gravity and seamlessly resumes target speed tracking and yaw angle tracking. In conclusion, the key finding of this project is that deep reinforcement learning provides dynamic 3D resilience that classical PID controllers simply cannot achieve due to unmodeled physical cross-coupling. Beyond the final model, we also performed a thorough comparative analysis, working through various reward functions and benchmarking PBO against SAC and DDPG. We also conducted an extensive grid search for learning rates and discount factors. You can find this in the PDF project report. This is all I have. Thank you.